Okay, so let me move on now. So now I know that if I have a VCCS, the output is only going to charge exponentially like this, and the let me write it, V out of 0 plus was 0. In steady state it reaches delta V. Similarly, at 0 plus the current was Gm delta V, and the current in steady state is 0, and time constant was CL by Gm. Whereas if this was an OTA, it would have jumped instantaneously like this. So now that we know that with an OTA the output is only going to charge slowly, we kind of have a metric to quantify how fast this is responding, and the way we look at it is to observe what is the maximum rate at which the output can rise. Again, this is time. So at what time instant do you think the output slope is maximum here? This is the output exponentially rising curve. At what time instant is the output slope maximum? 0 plus. So that means that we look at the slope at 0 plus. And what do you think is that slope at 0 plus? I mean, one thing is to take the output equation, differentiate it and put t equal to 0. But remember that at 0 plus, I know the current. What is the current? Gm delta V. So at 0 plus, if I look at it, I have a case where a current of Gm delta V is charging the capacitor CL. So what will be the slope? If a current I charges a capacitor C, what is the slope? I by C. Okay. This is Gm. Cool. So again, here we have considered an ideal OTA. So which means here it looks like if I keep increasing delta V, even the current at t equal to 0 plus will keep increasing. So I'll rewrite it like this. This is I out of 0 plus by CL. Yeah, so here looks like if I keep increasing delta V, even I out can increase to whatever value it wants. But in our OTA, the 5-transistor OTA, we know that we have a finite current. So let's see what will happen. Let me copy this. So let me try to make the same circuit. The OTA is going to be put in negative feedback. So let us say it's put in feedback like this, and then you have CL. So here please remember, this is the positive terminal, this is the negative terminal, so the feedback will happen this way. And I have CL here. And here obviously I will be feeding a DC voltage. I'll call it some VCM plus delta V, or let us say it could be VB, doesn't matter, some VB plus delta V U of t. Okay. So I will be applying VB plus delta V times U of t. And what will be the bias voltage at the inverting terminal? Only the DC bias voltage. VB, again virtual ground, so even the DC bias will be same. Is this clear? So I'll just say that the bias here is VB. Okay, so and we already know that the output slope is maximum at what time instant? 0 plus. So I'd only look at the circuit. This is essentially a snapshot of what's happening at 0 plus. Okay. We know at 0 plus the output is 0. That is a small signal V out to 0. So the total V out is the bias voltage VB. That's what I've written here. Okay. Huh.
So for this case, are we considering GM to be infinite?
No, finite.
We will still negative virtual ground work at finite GM.
No. This is the DC, right? With respect to DC, this would have been set. Fine. Now the DC operating point is established. Then I am making a small change, and I am seeing what's happening because of that, right? And that change has not reflected here yet, because I am looking at 0 plus. Only the input has changed. This has not responded yet, because I know the V out at 0 plus is 0. The small signal V out is 0. Okay, at 0 plus, what is U of t? The unit step 1. So I'll basically erase this. So now you look at this. I have M1 has a gate voltage VB plus delta V at 0 plus. M2 has a gate voltage VB. So which of the two currents will be larger? If I call it I1, I2. I1 is going to be greater than I2, assuming delta V is positive, right? But what can you say about I1 plus I2? That is fixed by the current source I0. So which means if I1 is increasing, I1 has to reduce to keep the sum to be a constant I0. Okay. So now let's say at 0 plus, again this is all at t equal to 0 plus, okay. If I keep increasing delta V, what will happen to I1 and I2? I mean, let us say for some delta V, I find that I1 is greater than I2. Now if delta V is greater, what can you say about I1 and I2? I1 will be more, I2 will be small. So if I keep increasing delta V, after some point what will happen? I2 will be 0. That's a like extreme case. So I'll say that at some delta V equal to delta V max, I2 will be 0. What will be I1? Is this clear? Again, this is at t equal to 0 plus. That instant, what's happening is what I'm looking. So I2 is 0, so which means M2 is just entering cutoff. Okay. And again, one thing to notice, see, M2 is entering cutoff because of the following, right? If the gate voltage here is increasing, this source voltage will also increase, right? So I will just say as delta V increases, Vx also increases, and at delta V equal to the delta V max, where exactly M2 is cut off, if M2 is just cut off, what is Vx then? No, it's not Vb. I mean, this should be just cut off. Vb minus Vth. Fine. So then I will say Vx is Vb minus Vth. When Vgs is equal to Vth is when we consider it to be cut off. Just a first order calculation. Okay. So this is what happens. So maybe I'll mark it here. The current here is 0. The current here is I0. So which means the entire current is flowing here.
Why did you say that Vx is also increasing?
Okay, good point. So the idea is, if think of it like this, right? This is like a common drain configuration, source follower. If you keep increasing the gate voltage, source will also try to follow. So now the entire current I0 is steered towards M1. So what can you say about the current in M3? Huh? That will also I0. Fine. Now remember, M3 and M4 form a current mirror. So what can you say about the current here? Now the current through M4 is I0. Here there is no current. So what is the current getting pushed into the capacitor? So the maximum current that the OTA can push to the capacitor is I0. So which means what is the maximum dV out by dt now? I0 by So what's happening is this, in the actual circuit, the current demanded by the capacitor at t equal to 0 plus is Gm times delta V, right? We saw already here, Gm delta V. But if I keep increasing delta V, at some point what will happen is the current demanded by the circuit will be much greater than the current present in the OTA. So the OTA, what it will do, it will take the entire current and push it to the capacitor to charge the capacitor. Okay. So now I have a constant current I0 getting pushed into a capacitor. So how will the output change? So constant current is getting pushed into a capacitor. How will the capacitor voltage change? Linearly, right? So that is the implication of this. So this is called slewing. And this slope is referred to as the slew rate. In particular, we'll call it slew rate positive because I have taken a positive delta V. Now similarly, you can find the slew rate if the step was negative, and you can work out even the negative slew rate will be same as I0 by Cm. Basically, if I apply a negative step delta V, now M1 will be cut off and the entire current flows through M2. Thus the things change. So now
say that I not gets copied instantaneously.
Instantaneously meaning?
I mean, all this is happening at
0 plus, yeah, everything is happening instantaneously. I mean, remember, if there is no capacitance, there is no delay. Things will happen instantly. Yeah, of course, in practice, if you go to like quantum level, yeah, there is some delays, blah blah blah. But at the level we are looking at, this is all happening instantaneously. Okay, so as we saw, the implication is the following. So ideally, if I have an ideal OTA for, let us say, some input delta V, the output would have been exponential. Now if I have a larger delta V prime, the output will be a scaled version of this, right? Again, this is time, this is V out. Now if I have this 5-transistor OTA with a finite current I0, for small delta V, it would have been fine. It will still follow what will happen with an ideal OTA. Because for small inputs, the current will be smaller than the current present in the OTA. So the OTA can nicely support the current. Now let us say this delta V prime is greater than the maximum delta V. So which means at 0 plus, the actual current demanded by the circuit is much larger than the current in the OTA. So now the output will no longer follow this exponential behavior. As we saw, the current is constant and that constant current charges the capacitor. So how will the output change? Linearly. So maybe to make it more clear, I'll show it like this. So now the output will change linearly like this. It's a linear slope. So now tell me, I mean, this is a t equal to 0 plus. Now do you think M2 will always be cut off, or it will turn back on after some time? Or when will it, I mean, why will it turn back on? Huh? Why will Vx decrease? Output voltage? Yeah. So as he's saying, remember, as of now, M2 is cut off because Vx is sufficiently large, right? Now as current charges the capacitor, the gate voltage here will start to increase, and once it reaches a sufficiently large value, this will start to turn on. Clear? So that's what will happen. It will increase linearly till M2 starts to conduct. Okay, so let's say at this point M2 starts to conduct, then everything will be in saturation. Then you will have the linear, the exponential settling behavior like this. So this part is linear, and this is what is called as slewing. And the slew rate is essentially I0 by Cm. So which means now let us say I have a case where I apply an input which is 2 times delta V prime. Okay. To make it to scale, let's say it's 2 times delta V prime. again at t equal to 0 plus, do you think the OTA can support the current? No. So what will happen now? The same thing will happen. The entire current I0 will be pushed to the capacitor. So initially the output will again follow the same behavior. Okay. Right? And now I am having a larger step delta V. So which means Vx would also be larger than before. So do you think M2 will turn on after a longer time, or it will turn on faster? It will turn on after more time, right? So let us say now it will go with a linear slope for, let us say, more time, and after this point it will, let us say, do the exponentials. Clear? So now tell me, is this slewing process resulting in a linear input output characteristic or a non-linear input output characteristic? Maybe to simplify it, see, let us say I have an input delta V prime, I have an output like this, I scale the input by a factor of 2, but the output is still following the same curve and then does this. So is this linear or non-linear? Why linear?
For a longer time it is showing linear behavior.
No, okay. Here what we mean by linearity is this, right? If I apply an input delta V, I get some output. If I scale the input by some factor, if it's a linear system, what should happen? The output should be scaled by the same factor. Is it happening here? No. Fine. So this straight away results in non-linearity. So one last thing, let's quickly calculate what is this delta V max so that we know what is the limit. So let me copy this. So I'll erase all this. Yeah. So let us say I am operating at the exact delta V max where the current in M2 is just becoming 0. That is, M2 is just become cut off. And at that delta V max, I know my Vx is Vb minus Vth, and this is essentially the gate to source voltage of M1. And what is the current flowing in M1? I0. So I can call it as Vgs of M1, the current I0. Okay. So if I write it, Vgs of M1 at a current I0, that is the gate voltage. What is the gate voltage of M1? Vb plus delta V max minus the source voltage, which is Vb minus Vth. Okay. So from this you can calculate. So here Vb goes off. So my delta V max is, so what is delta V max from this? No, it's not Vgs plus, Vgs minus Vth. Okay, so this is Vgs minus Vth at a current of I0. So I'll write it as V overdrive of M1 at a current of I0. Okay. So nominally, what is the bias current through M1 and M2? Nominally, what should be the bias current through M1 and M2? I0 by 2. So how do you think this is related to V overdrive of M1 at a current of I0 by 2? I mean, remember, overdrive voltage is square root of 2 times the drain current by whatever mu C Ox W by L. So let us say for ID equal to I0, you have some voltage. If it is I0 by 2, how is this related? Square root 2 times. So that's the maximum voltage. So the moment you have delta V exceeding square root 2 times the biased, nominal overdrive voltage of M1 or M2, the current in one branch will become I naught, and the other branch it will become 0. Is this clear? So let me show it this way. So what it means is the following. So let us say if I plot a curve like this. In the x-axis I am plotting delta V. In the y-axis I am plotting delta I, which is I1 minus I2. If delta V is 0, what can you say about delta I? 0. If both gate voltages are equal, the currents in the two arms are equal, it is 0. For small changes in delta V, delta I will be, how will delta I be related to delta V? If I make small changes to delta V, will the current be linear or non-linear? Huh? So what I am saying is, if I have this, I make small changes in the gate voltage delta V. So how will be the small signal currents? Linear. It's a small change, right? So again, it's Gm times delta V. So you'll have slope like this. Now the moment I exceed that delta V max, which is square root 2 times the overdrive at a current I naught by 2. At this point, what happens to the differential current? What value it will become to? I naught. Okay. So at this point it saturates to I naught. Similarly on the other side it becomes minus I naught. So here also it's the same, it's minus square root 2 times the overdrive voltage. Okay, cool. So I'll stop here now. So since we have some 5-6 minutes, I thought I'll discuss one or two problems from the problem set. Okay. So maybe one problem I wanted to discuss was this. So let's see if I have time to do that. So this was one problem where you were asked to find the resistance. Okay. So the way I would ask you to do is the following, right? So first, let us say this is some RD. As I mentioned, you first try to ignore non-idealities here and try to find the resistance. So here you can ignore R naught. So let us say I don't consider R naught. To find the resistance, you apply a test voltage here. So this is also V test. What is the current? So what is the resistance now? I apply a voltage V test. It seems like I draw current of Gm times V test. Resistance is? Right. So now you at least know, now you at least know if I don't have R naught, the resistance is 1 by Gm, right? That should be trivial. So now even if you include R naught, you'll have to calculate now, but maybe you can do a smarter calculation like this. I don't know if this is smarter, but what I would do is this, right? So let us say again you apply test voltage. So now we can think of it like this. I apply a test voltage here as well as a test voltage here. Both are same. And I have to find the currents flowing in both the sources. Fine. What can you say about the current flowing here? So I don't have to worry about this fellow. I only have to worry about this current. Now this is a small signal linear circuit. I seem to have two inputs. What can you do? So let us say first consider only due to the source applied at the drain. The voltage source connected to the drain. So here you apply V test. This is RD. So what is the incremental equivalent of this fellow? R naught. VGS is 0. There is no GM VGS component. So you only have R naught. So what is the test current now? I just have RD and R naught in series. So the test current is RD plus R naught. So now I will take the other case where the test voltage is applied at the gate alone. Test voltage is applied here. So this is RD. If I apply a test voltage V test, source is incrementally ground. What is the incremental current? GMVT. Now remember, this GMVT also has two parts to flow. I am interested to find this current. So how will you find? current division. So this current is GMVT times what is the factor? R0 by? That's it. So what is the equivalent resistance now? I mean, you can write RD plus R0. I mean, this way, look at it. I didn't write KCL at all. This is how you build intuition, right? I mean, writing KCL and finding is one thing. If you do it this way, you know what's happening to what current, how is it flowing, and etc. But you don't stop here, right? So you see, this is the expression you get. Does it remind you of some expression you have seen before? Huh? Yeah, if you recollect, even if you had a case like this, RD, this would have been the same, RD plus R0 by 1 plus GM R0. Now looks like this resistance is same as the resistance I have looking here, right? Of course, now you can think, now you should think why that makes sense. Well, the way you can think of this result is this, right? Here I have grounded gate and drain. I can think of it like this. I have both of them connected. This is connected to ground. So basically what I have is this fellow. Two terminals A and B. In one case, I am grounding the terminal A and finding the resistance looking here. In the other case, I am grounding the terminal B. I am finding the resistance looking here. So here, how many terminals I have? So I have two terminals. So how many port network is this? One port network. If I have one port network, to characterize this linear one port network, how many parameters I will need? One. I mean, remember, if it was a two port network, you will need basically 4 parameters. If it's one port network, I'll just apply a voltage and find what is the current. So I have only one parameter, and that parameter is essentially the resistance or the admittance, right? So this is now a two terminal device, which means I can model it using a series impedance Z. That's it. Now if you have an impedance Z, it doesn't matter I ground this terminal and find the resistance here, or ground this terminal and find the resistance here. Both will be, I mean, the moment you have this, other problem should kind of be easier. For example, now if I have a case where I have some, I don't know, Rx, and then I do this to you. Sorry, just a couple of minutes. Let's see if I can finish. So what is the resistance looking in now? Yeah, now you know this entire fellow is one resistor. It is a two, I mean, this is basically a two terminal device or one port network, which can be modeled by an equivalent resistance if it's linear. So this is simply Rx plus R equivalent. This is basically R equivalent. Similarly, if I have a case like this, this is incrementally short. What is the resistance looking now? I mean, this you can replace it like this. I have this guy and then R equivalent. This is basically the cascode configuration. Now you should write it in one shot. So this is what, I mean, this is how I want you to build intuition, right? It is not just, I mean, it is nice to basically draw the small signal KCL, KVL and solve for it. But don't stop there, right? As we saw in the first class, you try to make sense of results. 10, let us say GM to infinity, R to infinity, 0, make sense. And if you get a result, see if you have seen that result somewhere earlier and try to correlate and get that intuition, okay? I'll want to show maybe one other problem. Just 1 minute, let's see if I can do it. Let's say I take this. Again here, see if I were to compute this, right? Again you can use KCL, but what I will do is the following. If you apply small signal Vi, what is the small signal current flowing here? GM2 times Vi. Now this current can flow in 3 parts. Now I see R0 is in parallel with Rx. I'll basically get this over with. Now it's clear. I have GM2 Vi that can either flow here or here. And what is the resistance looking here? It is 1 by GM because I have shorted the drain. Okay. So now I have GM2 Vi that can flow either towards 1 by Gm or to Rx parallel R naught. So you do the current division, that is basically this, right? 1 by Gm1, okay, I mean, this is what I would want you to do. See, I mean, for the exam, yeah, I mean, you draw the entire small signal and do it. If you are fast enough, you'll be able to calculate and get it. That's not a problem. I'm okay with that. But to be a better analog designer, you need to build intuition, right? And this is how you get this, right? This gives a qualitative feel for what's happening in the circuit. So what's happening is this voltage VA is getting converted to a current, and the fraction of that current is getting pushed here. So please do it that way. And one thing I want to say is, I find this multiple times in every quiz when I conduct. There are 3-4 students who make this mistake. Let us say find something like this. The small signal current is not GMVI. Okay, what is it? Yeah. So a lot of times in hurry people write it. In every quiz I have seen at least 1 or 2 students do this all the time. So please make sure like you are careful. So I'll stop here. I don't have time. Please.